Most students looking at the homework assessment for 4.3. And the homework, I've got questions 2 through 9, 12 through 16, 18 through 21. So a little grouping of questions there. First one is colored rods. After that, it's find the GCD and the LCM using the intersection of sets method. Number 3, using prime factorization, using the GCD with the Euclidean algorithm. I believe these mirror each other pretty well in this assignment. Yeah, they seem to match up pretty well. Find the LCM using any method. Okay, so again, if it's close to prime factorization, maybe use prime factorization. And maybe we'll take a look at a couple of those. The product is this, the GCD is this, GCD is this, product is this, got it. Okay, so then classify which of these are true or false. And again, true or false, when you see true or false, understand I'll probably ask you always, sometimes, never questions. So be aware of that. Let's see here. What else did I say? 2 through 9, 12 through 16. So yeah, this is a three group. That's fine. 12 through 16, find 3 pairs such that the LCM is 60. Find all whole numbers such that this is true. Light has 3 colored intervals. This many times, this many times. When does it actually all flash together? Okay, those are all reasonable questions involving these. 16 and then through 21. Okay, so then some word problems at the end. Okay. All right, let's take a look at some of the initial ones that are a little bit more computational in nature. So let's see here. So intersection of sets. I did this if you watched the main video for the section, but why don't I go ahead and we'll do just a couple of these as well. Let's see here. All right. So it says find them using the intersection of sets method. So what that means is find the GCD and the LCM. So if I was doing something like 20 and 36, I would put divisors of 20, and I would make a set of all the divisors of 20. So I know I have 1 and 20. I know I have 2 and 10. I know I have 4 and 5, and that's it for 20. Okay, and then I would put the divisors of 36. And for 36, I have 1 and 36, right? I have 2 and 18. I have 3 and 12. I have 4 and 9. And then I have 6 and 6. So there they are. So this is the sets for divisors, and then you would find the intersection of those. So the intersection of those would be, let's see here, a 1, a 2, there's a 4 in both. I see. So 5 and 6 don't match, 9, 12, 20. So that's it. So that would be it. So the GCD of 20 and 36 is 4. And then you would do the same for the least common multiple. So the least common multiple, that means I would do multiples of 20 and multiples of 36. Okay, multiples of 20 would be 20, 40, 60, 80, 100, 120, 140, 160, and dot, 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 dot. I'll just do dot, 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 because it keeps going, obviously, for a while. Let's see here, 36, 36, 72. And again, if I need to, and if you need to at home, just grab your calculator, type in 36, and then say plus 36, and then plus 36, press equals, equals, equals. I get 108, I get 144, I get 180, and I can see I should have kept going a little bit more up here. Woohoo! Let me put a 180 in there because that's the next number. And then I can keep going from there. But when I finally find something that matches up, I know that would be the multiple. So multiples of 20 intersect multiples of 36. They would start at 180, then they would go 360, then they would go 540, and it would just keep going from there. So that's why the least common multiple of 20 and 36 is 180. And again, that's because they asked you to do the intersection of sets method. Again, that method works really well for smaller numbers, and you can see 20 and 36, they're not, I mean, they're not that big of numbers, but already it's starting to get problematic to use this technique. All right, let's jump back and try a little bit more. Well, let me clear all those, and we'll move down to question 3. Now it says use the prime factorization method. All right, well, I like that one as well. And so again, I'm not going to do all of them, but I'll pick, oh, I don't know. What do I want to? Okay, I'm sure some of you are like, oh, he's never going to do the tough one. All right, I'll do part C because it has 3 pieces. But again, it doesn't really matter as you go through it. 96, I can see 9 plus 6 is 15. That means a 3 is there. It's also even, so I know there's a 2 is there. So 96 is going to equal 6 times, looks like 16. It gives me 60 and 36. That works perfect. And so 16 is 2 to the 4th. And I have a 2 times 3 right here. 2 times 3. This is 2 times 8, which is 2 cubed. So I end up with 2 to the 5th times 3. Okay. 2 to the 5th is 32. So 32 times 3 works out perfect. So there's prime factorization there. Now I come down to 900, which, again, don't be too strict. 9 times 100, right? 9 times 100. And 100 is 10 squared, which would be 2 squared, 5 squared, and 9 is 3 squared. So there's a 3 squared. And let's see, now the number 630. Okay, so 630 is 63 times 10. 10 is a 2 times 5. 63 is a 9 times 7. So that's a 9 times 7. Now, all I'm going to do is rewrite these so that they are in ascending order. Times 3 to the 1st. The next one is 2 squared, 3 squared, 5 squared. And the last one is 2 times 3 squared times 5 times 7. Okay. And now I'll use a different color to say for the GCD, what am I looking for? The GCD, I guess I'll write it all the way out, which would be the GCD of 96, 900, and 630 is the smallest exponent that goes into each one. So it has to exist. So for the 2's, the smallest number would be 2 to the 1st. For the 3's, the smallest number would be 3 to the 1st. And after that, I can see there's 5's, but there's not a 5 in all of them. So if you needed to, you could put a 5 to the 0 and a 7 to the 0 if you wanted to kind of match them up. I don't think it's necessary because if it doesn't exist, don't write it. So my GCD is 6. And I'll choose a different color here for the least common multiple. Least common multiple of 96, 900, and 630 is the largest. So I know there's a 2, the biggest is 5, so 2 to the 5th. In the 3's, the biggest is 2, so 3 squared. In the 5's, the biggest is 2, so 5 squared. And in the 7's, the biggest is 1, so times 7. And that would be it. This is perfectly fine to leave in factored form. If you really wanted to multiply it out, now let's see here, you have 32 times 9 times 25 times 7. So if you really wanted to write it all the way out, feel free to. It's 50,400. Okay. So that's, again, the prime factorization method. Once you get them prime factored, this is by far the easiest method. However, it's just getting them prime factored. Sometimes it's a little harder. Oh, let's see here. So we want to do Euclidean algorithm. All right. So we'll do Euclidean algorithm. And the next one actually says find it for any of the methods. I'm not going to go through. I'm not going to go through that one. Let's see here. We'll erase that piece, and there we go. All right. So it doesn't really matter to me which one we pick. I'm sure that some of you are like, pick the big numbers so I can see how it's done. It's going to be about the same. As a matter of fact, the closer they are like this, you can tell the first one's just going to be that it'll go in one time. Okay, but I will do the bigger numbers so that you can see it. That's not the big issue here. So again, what I need is I need a number that divides both of these. And if it divides both of them, it has to divide the difference. And so what I'm going to do is I'm going to start by saying 14,595 is equal to a certain number of 10,856s plus a remainder. And so I can see it only goes in one time. And so now I do my calculator to do 14,595 take away one group. So clear 14,595 minus one group of 10,856. And that leaves me here with 3,739. Okay. Now, what do you do with those? You bring them down and you repeat. Okay, so 10,856 divided by 3,739. Okay, so now I end up, if I do that division, I get 2.9034, which is like, oh, it's so close to being 3 times. So what I'm going to do for this problem is I'm going to do it both ways. I'll do it with the 2, kind of the way the book method showed, and then I'll come back and I'll do it with 3 because I think it's actually a little bit easier if you do it with 3. So here we go. I do 2 times this. Okay. So now I would say 10,856 minus 2 times 3,739, and I get 3,378. So what do? I simply bring those numbers down and repeat. So 3,739 equals, I can tell you it's going to be one group of 3,378. Oops. So, and then plus a remainder. Okay, and I get 361 as my remainder. And then again, all I do is I just keep bringing them down. Bring them down until I can see the answer. I can see what's common to both numbers. I can't right now at this point, at least I don't see very quickly what the answer is. So let's see here, 3,378 divided by 361, and it says 9.3, so that's 9 whole times. So 9 times 361, and subtract that from 3,378, and I get 129. Keep going, repeat, wash, rinse, repeat. 361 is equal to, so your 361 divided by 129 is 2.79, so 129 goes in 2 times, and let's see here. So 361 minus 2 times 129 gives me 103. Okay, and then I would continue. I'm going to have to continue over here on the left-hand side. So now I have 129 equals, I can tell you it's one group of 103, and that leaves me with 26 left. Keep going. 103 equals, how many groups of 26? And 3.96. So that means three groups of 26 plus a remainder. 103 minus 3 groups of 26 gives me 25. And at this stage, I would stop because I can tell what's common between 26 and 25. And the answer is just a 1. There's nothing else in common between them. But if you kept going, you could say it's one group of 25 plus 1. Bring the 25 down. You get 25 is 25 groups of 1 plus a remainder of 0. And as a reminder, whatever your last remainder is before you hit 0, that would be your GCD. So the GCD here is 1. Okay. Now I did mention, hey, if it's quicker for you, go up and do it with, like, round up. Like here, we rounded to 2.9034. We rounded it to 2. You could turn it into a 3. You're just going to be over a little bit, so you would turn this into subtraction at the end. The theorems in section 4.2 didn't care if it was addition or subtraction. So let me show that just for those of you who are kind of like, hey, I don't want this to take forever. Can you show us a way that may not take quite so much time if we have to do this technique? And let's see if we can do that. Okay. So 14,595 is equal to one group of 10,856. We know that, plus, oh shoot, I should have written that number down. 14,595 minus 10,856 is 3,739. Okay, so here I go bringing it down. 3739. And how many groups of this? Let's see here. 10,856 divided by 3739, and I get 9.203. So I'm going to put in 3 groups of this. Now, when you multiply 3 times, if you do 10,856 minus 3 groups of 3739, you're going to end up with a negative number over here, and it is negative 361. But what's great is positive or negative, the number can just come down because we're talking about divisors. So we can just bring the 361 into play now. So 3739 divided by 361 turns out to be 10 of these. So 3739 minus 10 groups of 361 turns out to be a plus 129. 361 divided by 129 is 361 is equal to 129. Now my calculator says 2.79, which is way closer to 3. So I'm going to do 3 of them, and then I'll just subtract. So 361 minus 3 times 129 gives me a 26. Okay. So then I can bring down 129 and say how many groups of 26 are in here. 129 divided by 26, and I get 4.96, which is, here's my shot. Put in 5 of them, and then you do 126 minus, what is it? Minus 5 times, 129. 129 minus 5 times 26, and I get minus 1. And here's a big fun fact. Anytime you hit 1, the next thing's going to go in perfectly, because it'll be 26 is 26 groups of 1 plus 0. But anytime you hit a 1, your GCD is 1. So notice, by using the ability to go with pluses or minuses, 1, 2, 3, 4, it took me 5 steps instead of 8 or 9 steps. So you're in charge of this problem. If you'd like what I just showed you here, feel free to use it. You can go up or down when you do the divisions. Okay. Let's see here. The product of 2 numbers is this. Their GCD is this. Remember, the GCD times the LCM is equal to A times B when you have 2 numbers. So that's what question 6 and question 7 is saying. Question 8 is, if the GCD is 1, find the LCM. Oh, huge hint here, right? The GCD times the LCM is equal to A times B. So if the GCD is 1, then the least common multiple is just the 2 numbers multiplied together. Okay. Let's see here. Now you're finding a GCD of 2 numbers with themselves, a GCD of A squared and A. Big hint, think back to what we were doing with prime factorization. All those techniques are going to be useful here. Classify as true or false. If the GCD is 1, then A and B cannot both be even. Well, let's see here. If both of them were even, then the GCD would have to be 2. So I like the way they're thinking. And you could have rewritten that if-then statement as the contrapositive, and it might have made more sense. If A, let's see here, A and B cannot both be even. So if that is not the case, if both of them are even, then the GCD is not equal to 1. And you'd be like, yeah, the GCD cannot both be equal to 1. Let's see here, GCD is equal to 2, then both A and B are even numbers. I wonder about that, right? If A and B are any even whole numbers, then the GCD has to equal 2. So if the GCD is 2, that makes them even numbers. If they are even numbers, is the GCD have to be 2? So what an interesting question, and one that I will leave to you. Let's see here. What else do we have? Find 3 pairs of numbers such that the least common multiple is 48. Don't go too deep into this. I know sometimes some of you spend a lot of time on a few of these problems. If the least common multiple is 48, think about 48 with its prime factorization. 48 is what? 4 times 12, which is the same as 4 times 4 times 3, which is 16. So 2 to the 4th times 3 to the 1st. Now you need to have 2 numbers that multiply here, right? And so these have to be numbers that both of them are smaller than what you started with. So that would have to be the LCM. So the LCM, you have to pick the biggest one. So each one of these have to have some 2s, or at least could have some 2s in it. So here's A and B. A could equal, this is where It just says 3 pairs of numbers. So I could have A be 2 to the 4th and B be 3 to the 1. That's one answer. The next answer would be A is equal to 2 squared and B is equal to 2 squared times 3. Oh, I need the biggest one here. So I need 2 to the 4th times 3 to the 1. Okay. So that way the biggest one is chosen for each of those. There's another one. There's a lot of options here. And let's see here. Yeah, I'm just going to go cheesy. 2 to the 4th times 3 to the 1, and B is just the number 1. Because then the LCM is just the product of the two numbers. So it works out pretty nice. So again, there's a couple you can choose. You just have to choose things that will, don't pick a 2 to the 5th, because that would be bigger than 2 to the 4th. But you can pick any group of 2's less than that, and any group of 3's that has either 0 or 1 of them included. Very quick. All right. Let's see here. I think the rest are kind of word problems. So I'm not sure if we want to do a ton of those. But I mean, a question, just so you're kind of understanding, these questions are going to relate to the concepts that we're learning in this section. So if we talk about this problem with motorcycles and they're crossing a circular course, and so basically they're driving around in circles and racing, sure. And basically there's a fast, kind of a medium and a slow, but they kind of, because of the way that they take their laps, it's possible that they all come across at the same time. Maybe they start at the same time, maybe they just hit a lap at the same exact time. And then if they keep that exact same pace going, the first passes the starting point every 12 minutes, the second every 18 minutes, and the third every 16 minutes. So what we need is, if the first one crosses every 12 minutes, then it crosses at 12, 24, 36, right? 48, 60 minutes, 72 minutes, right? And as you think about this, you could say to yourself, well, the other third person is every 16 minutes, right? 48, was that 64, 80, 96, dot, dot, dot. And so basically I'm saying, ooh, so every lap, every 16 minutes, that's finding multiples. So I need multiples of 12. I need multiples of 16 and multiples of 18. And at some point in time, those should match up. Now, these three numbers are pretty small. So if I was doing this, I know I'd be looking for the how many minutes will all three pass the starting line again at the same time. It doesn't say what's the shortest amount of time. So I would be giving all of the answers for this one. So I would look at 12 and I'd say 12 happens to be 2 squared times 3. 18 happens to be 2 times 3 squared, and 16 is 2 to the 4th. So the least common multiple of these times of 12, 18, and 16 using prime factorization would be 2 to the 4th because it's the biggest amount of 2's, and 3 squared because it's the biggest amount of 3's. And so my final answer there would be, let's see here, 16 times 9, which is 144. So after how many minutes? After 144 minutes. After 144, then after 288, then after, and dot, dot, dot. Because remember, once they pass at 144, if they keep going around at the same rate, they're going to pass again in another 144 minutes and another 144 minutes. Okay. So you could write down 432. You could keep going. 576. Dot, 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 dot. 720. Dot, 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 dot. Because it just says after how many minutes will all three of them pass the starting point at the same time. Something like that always reminds me of the TV show that The Office, when they were watching that little box that keeps hitting and bouncing and bouncing and bouncing. I think we'll do an in-class activity kind of like that. With a pool table, doop, 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 and it just bounces off the walls. And eventually it hits like right in the corner, just like right on. And so that's kind of what that reminds me of. It's rare, but it'll happen. All right. So I think that should about do it for getting you started on the homework set for 4.3, our last one before the test. All right, off you go.